Hello, my name is Ben Wewell, and I will be discussing advancements in the nuclear and fossil fuel power generation industries and the effects they have on the nuclear renaissance. Nuclear power companies have developed new reactors in response to problems like the high initial cost of plant construction and how to prevent nuclear accidents like Fukushima from happening again. One such example is General Electric's Economic Simplified Boiling Water Reactor, or ESBWR. The ESBWR's passive safety features allow it to cool itself without the need for external electricity supplies or human intervention. The ECCS of an ESBWR consists of four subsystems aimed at protecting the integrity of the reactor. These subsystems include the gravity-driven cooling system, the isolation condenser system, the standby liquid control system, and the automatic depressurization system. The gravity-driven cooling system is equipped to inject large volumes of water into the reactor pressure vessel to keep the fuel bundles covered. The isolation condenser system removes decay heat following a reactor shutdown and isolation. The standby liquid control system provides water in a loss of coolant accident as well as being a backup method for maintaining subcriticality as the reactor cools. The last subsystem is the automatic depressurization system, which depressurizes the reactor to enable makeup coolant to enter the reactor vessel. Earlier this year, the NRC allowed Dominion to build an ESBWR in North Anna, Virginia. Other companies have not pursued this design because of high construction costs and a limited number of areas to place this 1500 megawatt reactor. Small modular reactors, another advancement in the nuclear field, might be the future of nuclear power to tackle problems still needing to be addressed. Small modular reactors are reactors generally 300 megawatts or less and have benefits like greater efficiency, lower capital investment because of shorter construction times and less materials, the ability to increase manufacturing in the United States, and siting flexibility. Siting flexibility is the ability for SMRs to be situated in areas that lack the infrastructure to support a larger unit. Areas that lack land or water to support larger units will be open to the smaller design. There's also flexibility in the fact that they can be placed on sites of decommissioned coal-fired power plants. Many of the designs for SMRs are based on the ideas brought from typical nuclear reactor designs. However, because light water SMRs will have the least number of regulatory hurdles to jump of any of the designs, this is the most viable option in the United States. NuScale has been working to develop a small modular reactor that will produce 50 megawatts. This design allows for 24-month refueling cycles and a 60-year design life. Like the ESBWR, there is a passive system that can shut down the reactor in a safe manner. After the final review by the NRC, a NuScale reactor could be under construction starting in 2020 and in operation by 2023. Holtec International created a 160 megawatt commercial SMR named the Holtec Inherently Safe Modular Underground Reactor, or HI-SMUR. There are many benefits to Holtec's design, like a 1-week refueling outage needed every 42 months and the flexibility of fuels including MOX. Holtec International claims that their SMR can be built within 24 months and has an operational life of 80 years. Their application for design certification is planned to be submitted to the NRC in December of 2018. The NuScale's containment vessel is submerged in a water pool with the steam generators located above it. There are passive systems in place as part of their Highly Integrated Protection System, HIPS, for shutting down the reactor, not even requiring batteries to run on. The NuScale's design also claims that it will have the ability for black start capability. The future of the nuclear industry is focused around SMRs as the DOE plans to issue a multi-year cost-shared funding opportunity to provide a direct vehicle to support innovative domestic nuclear industry-driven concepts that have high potential to improve the overall economic outlook for nuclear power. In hopes to compete with other fuels in the power generation field, there has to be success on the SMR level, which it hopes to start doing soon. Fossil fuel has been creating designs to limit the amount of greenhouse gases they release into the air, increase their efficiency, and find effective ways of extracting fossil fuel from the ground. Advancement includes carbon capture systems, or CCS, combined cycle plants, and the shale revolution. The uptick in fossil fuel technologies could adversely affect the nuclear renaissance. As the support for climate change has been growing the past 3 decades, there has been a push to place taxes on carbon emissions. This has forced dirty burning power plants to either close their doors or adapt technologies that will keep them relevant in the future. The push for clean fossil fuel has led to new possibilities for plants by using CCSs that utilize 4 methods to prevent carbon from being released into the atmosphere: post-combustion, pre-combustion, oxy-fuel combustion, and coal-direct chemical looping. While CCSs are not new, reliability, safety, and cost have stymied an industry-wide usage until recently. The distinguishing factor between different types of carbon capture systems is when the toxins get separated from the fuel. Pre-combustion separates, removes, and disposes of CO2 before the combustion process. An important type is integrated gasification, which is gasifying coal with oxygen to yield a low-sulfur fuel gas. This was going to be used at the Mesaba Energy Project, but the project is currently stopped. Another problem is that it decreases the efficiency of the plant. Post-combustion removes CO2 and other toxins following combustion and before they are released into the environment. There are a handful of types like advanced solvents, solid sorbents, membrane systems, and novel concepts. While they can be retrofitted on pre-existing plants, they are expensive. Oxy-fuel combustion allows for a simpler way to capture CO2 by having pure oxygen created in a cryogenic air separator unit and mixed with the fuel in an oxy-combustion boiler. The CO2 and water are expelled from this process and sent to a CO2 purification and compression system. The coal-direct chemical looping system, or CDCL, is similar to oxy-fuel combustion, in which the coal is oxidized. The difference between these CCSs is CDCL performs the oxidation through an oxygen carrier like iron, copper, or nickel. CDCL has two vessels that use an oxidation-reduction reaction. The combustion side of the reaction occurs when coal, whether in solid or gas form, enters the reducer. This coal is oxidized by an oxygen carrier that enters the vessel. On the other side, air enters the oxidation chamber, is heated by the oxygen carrier, and expels hot air, creating steam. The oxygen carrier is regenerated in the oxidizer and used again. The CDCL design uses solid coal and can produce efficiencies over 90%, as seen by the 50 megawatt research plant built at Ohio State University. Another advancement in fossil fuel technologies is combined cycle power plants. Combined cycles consist of two parts, a gas turbine and a heat recovery steam generator, or HRSG. These plants are efficient, economic, and versatile in fuels. Gas turbines are broken down into three parts, a compressor, combustion system, and turbine. The compressor brings in air, pressurizes it, and forces it into the combustion chamber. The fuel is combined with the air and burned at high temperatures, which creates a hot gas stream that enters the turbine section. HRSGs recycle flue gas to produce efficiencies that approach 80%. After the hot gas is expelled from the gas turbine, it is directed into the HRSG. Through heat exchangers like economizers, evaporators, and superheaters, water is converted to steam to power a second turbine. The last development of fossil fuel is the birth of the shale revolution. This revolution was brought about by new techniques in drilling for gas and oil, causing the industry to boom. In hydraulic fracturing, or fracking, fractures in shales, tight sands, and coal bed methane formations stimulate the flow of natural gas and oil, which helps to recover a larger amount. A well is bored into the rock where massive quantities of fluid comprised of water, sand, ceramic beads, and chemical additives are pumped into them at high pressure. The rocks fracture and the sand and ceramic beads hold the fractures open. Horizontal drilling is not a new concept, but has led more companies to drill horizontal wells as they offer the most prolific oil wells. The benefit of drilling horizontally instead of vertically is that more oil-bearing rock is exposed. Horizontal drilling is like vertical drilling but is equipped with an incline ramp instead of a drilling mast. These methods can be combined to maximize the natural gas and oil removed. There are drawbacks to CCSs, combined cycles, and the shale revolution. CCSs, while helpful in cutting emissions, also decrease the plant's efficiency. The Mesaba Energy Project, which was supposed to resurrect coal, has failed, leading to more woes. Meanwhile, the shale revolution will be short-lived and has its own share of environmental problems. Shale gas is not inexhaustible, and the availability of it will be limited by the number of drilling locations in the U.S. Fracking has opponents because of the possibilities of contaminating water sources. As the current trends outside of the unproven CDCL design, coal is failing behind and their void is being filled by the natural gas industry because of combined cycles and cheap gas prices. For every annual decrease in the total output of coal fuel, there's been an equal increase in the total natural gas energy output. The increases in natural gas-fired power plants will equal out the number of coal-fired plants being decommissioned, therefore having minimal effect on the future of nuclear energy. Thank you for your time. I'd like you to now turn your attention to Daniel Ross, who will be discussing how the regulations make nuclear power plants expensive to build compared to other sources, a carbon tax, and the NRC rule and license process.